Hello and welcome to the pre-talk for the ANTS conference 2020. My name is Bogdan Dina and the title of our talk today is Genus 3 hyperelliptic curves with complex multiplication via Shimura reciprocity. This work is a common work with Sorina Ionica from the Universität of Picardie in France. Before introducing our main problem we would like to solve, we need to introduce some notation. We denote by CM2 a certain class field as an extension of this number field here, which we denote by KR. And the CM2 is a certain subfield of ray class field modulus 2. Further, we denote by lambda I the Rosenheim invariance of a hyperelliptic curve of genus 3x over the complex numbers. The main problem is stated following: having a hyperelliptic curve of genus 3 over the complex numbers with a complex multiplication by a number field, sextic number field k, and this Galois extension here. Compute the Rosenheim class polynomials hi of t. I will split this problem into three smaller subproblems, which I will introduce in a couple of minutes. We should mention that there is some previous work in this area, which was done by Weng 2005 and followed by Balakrishnan, Ionica, Lotta, and Vincent in 2016. The main objects today are a complex hyperelliptic curve of genus 3, which are subvarieties of the projective plane with an affine model of this form: y squared is equal to f of x, and f is a degree 7 polynomial with complex coefficients. Further, x is a cycling covering of P1 of degree 2 and ramified in 2G plus 2 points, the blue points, and I marked by yellow the ramification points corresponding to the Weierstrass points with x coordinates, the roots of f. We are interested in a certain model for x, which is given by the Rosenheim form. This is a model, an affine model of this form with lambda I complex numbers. And it is known that every hyperelliptic curve of genus 3, in this case defined over the complex numbers, can be transported via automorphisms of P1 into a curve in Rosenheim form. Before introducing the first problem on the way to solve our main problem, we denote by A3 the Moduli space of principally polarized abelian varieties of dimension 3, as well as by M3 height, the 5-dimensional coarse Moduli space of curves, of hyperelliptic curves of genus 3. Problem 1 is giving a simply moduli point in A3, whereby simply means that it's not isogenous to a product of lower dimensional abelian varieties. The question is this a hyperelliptic point? That means, do we find 7 distinct complex numbers such that the representation is given by an equation of this form, whereby in the first round we do not put in account the ordering of this coefficients alpha I. The solution of problem 1 based on counting the even theta characteristics, whereby we understand an even theta characteristic is an element in a half z to the power 6 with pairing equal to 0 modulo 2. To every point in H3, we attach Riemann's theta function. In this case here, we are interested in with a half characteristic, and the value of this function at this point 0 is our theta constant. The solution to the problem 1 is based on the theorem of Kratzer and is stated following: having a simply moduli point in H3 in A3, and A is an hyperelliptic point for some hyperelliptic points in A3 in this moduli space, and counting the number of the even theta characteristics, which are 0 in set. This set has size 1. That means we have only one even theta characteristic which will vanish in set. In order to introduce our algorithmic solution to this problem, we will introduce some level structure on abelian varieties, and for that, we picking every point in H3 will determine a triple A, E, and nu, whereby A is a abelian variety with torus representation plus a principal polarization given by some Riemann form, and for our interest is a symplectic isomorphism nu from the set of points of order 2 into the F2 module z modulo 2 z to the power of 6. In this way, we will identify points of order 2 on the torus as vectors psi, reducing them modulo 2. We define the analytic moduli space of principal polarized abelian varieties of dimension 3 with this level 2 structure by the cosets H3 by gamma 2, whereby by definition gamma 2 is acting trivial on two torsion points. The solution of our problem is the algorithmic solution of our problem, which is a part of the implementation, is based on Course-Main theorem. Given an exegetic system which corresponds to an 8-tuple ordered 8 set of distinct characteristics, whereby the last one corresponds to 0, plus some additional properties which we state in our paper, the interpretation of these additional properties is that this set eta reduced modulo 2 will generate the whole two torsion points on the abelian variety as an F2 module. Course-Main theorem is picking a moduli point in A3. Then we have two equivalent statements: is that A is a simply moduli point, and there is an exegetic system eta such that the unique characteristic, which will be 0 in set, will be constructed out of this ordered set eta. Further, it is equivalent to having a moduli point in a moduli space of hyperelliptic curves of genus 3, satisfying our conditions in problem 1, and the point at infinity on X will correspond to the Abel-Jacobi map HP0 here. Further, this set eta will fully describe our symplectic isomorphism between the points of order 2 on the Jacobian, and z modulo 2z to the power 6. With this, at the end, out of the algorithm of Poor, we will have a point in a moduli space of hyperelliptic curves of genus 3 with a level structure which is equivalent to a fixing of the ordering, a fixed ordering of the branch points, which is equivalent to a fixed homology basis of X. And we will identify the Weierstrass points as elements coming from the eta I. Problem 2 is having now these restrictions, this moduli point in A32, which is a hyperelliptic point for a curve in with a fixed homology basis and corresponding with a model of this form. Compute the Rosenine invariants of X, and for that, computationally we are using Takase's respectively Vincent formula, and we are computing the lambda I after normalization as an expressions in this the theta quotients. We should mention here that because of the only approximation of the theta function, this value will only be an approximation on the computer, which in the first round is by construction complex numbers, and by Shimura's theory we know that this element will live in this class field, which we denoted at the beginning by CM2. Having now our 5 Rosenine invariants of X, we would like to have a possibility to act on our abelian variety to compute the class polynomials. And this is given somehow. I sketched this here Shimura CM theory. We have a primitive CM pair, which is a tuple given by a sextic SEM field K and a CM type phi. With this, we can compute the reflex pair, which is a tuple also KR, which depends on the CM type and associated its associated CM type, reflex CM type. Since we are interested in points of order 2, we are picking the ideal 2, and on the other side we are computing for a certain group homomorphism, the ray class group of KR for the modulus 2. We are interested in this set of principal porous abelian varieties for a fixed CM type and a proper 2 torsion points, which we define here by prim K phi 2. And further, we know by Shimura CM theory that the Galois group of this extension here is isomorphic to this quotient, whereby the group H is more complicated, and we state in our paper. Having now a point in this set and an element of this quotient, we can, by Shimura, we are computing the conjugate CM point with an ideal in OK given by the first entry coming from a reflex type norm. The second parameter is the element which we will construct our polarization, and the third one is the proper 2 torsion point on the conjugate abelian variety. knowing now a way how to act on principal polar stability varieties, our third problem is stated following, having now a simply moduli point, which is a hyperelliptic point for for a point in this space of hyperelliptic curves of genus 3 with the level 2 structure. That means with this symplectic isomorphism in its Jacobian, and with the eta map, the fundamental exegetic system, for the period matrix Z, which will encode somehow the symplectic isomorphism. Having now this offset, the question is taking an element in this quotient, compute the Rosenheim invariance of the conjugate curve as an element in this space with the level 2 structure, and which is and the conjugate exegetic system for a period matrix corresponding to the conjugate abelian variety. Our solution is based on Streng's formulation of Shimura's reciprocity law, and he's giving us for every element in this quotient two matrices M and U with some relations between each other, one in the general symplectic group over Q, the other one in SP6F2. And we have a description of the computation for the conjugate Rosenheim, whereby the right side here will be a much more complicated formula, which we state in our paper. The one problem here is that having now this five conjugate Rosenheims, we can compute a model of the curve in several ways, because we do not put in account somehow the ordering of these points, which will have an effect on our symplectic isomorphism into its Jacobian. And for that to put everything somehow in a nice way together, we are doing some linear transformation here, beginning with this matrix. We are doing some transformation which will land up to some transformations given by some lifts of this matrix. We will compute a certain new point in H3, and to this point we will attach the conjugate exegetic system will correspond to the original one. That means we attached the symplectic isomorphism will respect here into this conjugate exegetic system, and with this by hand we can compute the conjugate Rosenheims for the period matrix for the new curve, and with underlying period matrix Z prime here out of our linear transformation. And I will skip the examples for the live session. Thank you for listening.